All right, in this module, we're going to start talking about what we call Brouwer or Kroger-Vink diagrams. These are diagrams that are going to use the Kroger-Vink notation that we've developed and the defect reactions that we've talked about in order to talk about concentrations as a function of partial pressure. And so specifically, we're going to look at oxygen. So let's look at one of these Brouwer diagrams and kind of get a feel for what we're looking at. So on the y-axis, we see concentration, and particularly log concentration, so large changes in concentration of various species like oxygen vacancies, metal vacancies, intrinsic vacancies here, holes, etc. And this concentration is a function not of temperature or something like that, but of oxygen partial pressure. And it really comes in three different regions that we see kind of separated by 1, 2, and 3. Excuse me. There's really no scale here. It's just kind of general ranges. And so over here on the left, we have the lowest amount of PO2. In the middle, we have what we would refer to as intermediate, and then high PO2 on the other side. And so these diagrams basically allow us to look at major trends to see what species are present and in relatively what quantities and how quickly they change. So the slopes here indicate how quickly they change in a given pressure range. And so these let us make some general conclusions about the different types of species that we would expect to see and so forth. And so in these next sections, we're going to go through and work our way through the different regions and see if we can more or less build this up from scratch and see how they're put together to kind of more fully understand where they come from. All right, so we are going to take a look to start at the low PO2 or low oxygen partial pressure region. And so this was the one on the left of the Brouwer diagram. And we've already looked at parts of this in the previous modules and looking at how an oxide responds to being in a low partial pressure atmosphere. And it does so through vacancies, right? We saw that before. So let's just rewrite that expression that we developed. So oxygen is in its proper sites, and then we get an oxygen vacancy, which has a +2 charge. That is balanced by the appearance of electrons, and then that oxygen that's neutral leaves in the gas phase. And so we have 1/2. So for each oxygen vacancy, we get a half of an oxygen molecule. So we know that we can define the Gibbs free energy for this defect reaction as delta G, and then we put RED, and this is not for the color red, but it's for reduced, because this is in effect being reduced. All right, so we also want to look at the mass action or equilibrium coefficient, and so that would be K red. And so this is going to be equal to the concentration or site fraction of vacancies, and then excuse me, the same for electrons squared because of the 2, and then we have PO2, and that's raised to the 1/2, and that's all over OOX. So again, this goes to 1 because we have we're assuming again a relatively small number of vacancies, and so this in effect goes to 1. And so that's what this leaves us with. And so this is also going to be equal to an exponential of minus delta G red over KT. So from this expression, this kind of also allows us to look at the question that I asked in a previous module about what happens if PO2 decreases, right? It shows that if PO2 decreases, then the oxygen vacancies would have to increase to compensate, right? Because this is a coefficient, this is a constant. So that kind of shows you it as well. This decreases, this has to increase to compensate. All right, so this is kind of what we're going to do for each of these regions in order to develop relationships that we're going to use in constructing the diagram. And so in the next section, we'll look at what happens in the high PO2 region.